the first intermolecular force we're going to look at is ion-ion interactions. So if we remember that the energy associated with ion interactions can be approximated as the same Coulombic interactions we find between positive and negative charges, which is simply the positive charge multiplied by the negative charge all over the distance that's between them. So if we look at what this might be, we have a positive charge ion, we have a negative charged ion, and we can say that there is distances. So this would be this is the radius of the positive ion, this is the radius of the negative ion, and the R value, R, is equal to R, the radius of the positive ion, and the plus the radius of the negative ion, or it's simply this distance, R. Okay, so R then depends on the ionic radius of each ion, so we have to be able to predict those using our periodic trends we've already learned. So the strength of ionic bonds, of ion-ion interactions, depends on the magnitude. So this is the primary we can look at. So magnitude of Q plus and Q minus, the charges. So it's the magnitude of the charges. Is it plus 1? Is it plus 2, for example? And we can see this mathematically in a sec. And then the second is the size of the ion. So if we have the same charged ions, we're going to try to find how the size differs, or smaller ions make stronger interactions, for this reason of the denominator having the R value. Okay, so let's go and look at a couple trends. So let's just do, let's take Li, and we're going to just do it in a series of halogens that are getting bigger as we go down. Chlorine, bromine, iodine. So we can see here that they're all plus, minus, plus, minus, plus, minus. So in this case, the charges are all the same for the ions. And so then size is the only thing that matters. So we can look at the strength of these interactions either using something called the lattice energy or the melting point. Now these correlate very strongly, they're different numbers. The lattice energy is simply looking at the amount of energy it takes to break up a series, a network of ionic bonds. It's calculated in a very nice way that we don't talk about until second semester general chemistry. But I will say that it is not the strength of a individual ionic interaction, but they trend exactly the same. So we can use them as a relative measure of strength and see that, and these are all in kilojoules per mole, that for LIF, we start off with 1017, and it goes down to 828 kilojoules per mole, down to 787, and then 732. Where the melting points, we'll see the same trend where we have 845, and this is in degrees Celsius. We have 610, 550. Now you'll notice these are pretty high temperatures, so I mean, you can melt salts, but it has to get pretty high, and so that's, you see sometimes people like cooking on their like big salt slab, because you can actually get a salt slab, for example, a piece of salt, pretty hot before it melts. So melting points and lattice energies both show that as if we label these as this is the smallest negative ion. This is the largest. So as R gets bigger, so R is increasing in this way, we see that the strength of those ionic interactions goes down. So that's showing this secondary size for the ion when the magnitude of charges are the same. Okay, if we look at, for example, difference in charges, so like NaCl versus MgCl2, we can see that if we can actually just calculate these proportionally or relatively. So we can say that Na has a radius, ionic radius of 102 picometers, that chlorine has a radius of 181. So we see this here. And again, when we see MgCl2, we are still looking at one interaction, even though it has two. And that is the same for NaCl. So we're just comparing the one interaction here. So we have R Mg2 plus is equal to 72 picometers. And we already have chlorine as 181. Okay. So what we can do is we can say, okay, so the relative energy of NaCl is going to be equal to Q1 or Q positive times Q negative, which is plus 1 minus 1. Okay. And then it'll be the addition of the radii 102 plus 181. Okay. So this is equal to 283. On the bottom, if you look at the relative interactions of MgCl, now it's Cl2, but we're just kind of looking at MgCl. That interaction that's going to be now on top. Mg is 2 plus, so it's plus 2 and then minus 1. But now you can already see the numerator is twice as big for MgCl2. That's why it's the primary predictor of strength. And if we look at the size, we see that we have the positive ion is 72 picometers plus 181. And so we see that this is going to be 253. So we've got, if we're looking at this, we have twice as big on the top. So this is 2 times as big compared to here. And we also see that the R is smaller. So both indications show that MgCl2 should have a larger ion-ion interaction. And it turns out that the magnesium chloride is more than 2 times as strong in terms of its, if you measure its strength as a measure of a physical property. So we can see here how magnitude of charge plays a bigger role than the size. And again, you only look at size when charges are the same. Okay, so we can use our knowledge for ion-ion and use that to determine the general strength. So let's just do a real quick example so we make sure we're feeling good about this. So let's say we have, I don't know. So we could do, we'll do it in black. So magnesium chloride and calcium chloride, let's compare those two. We could also say rubidium, bromide versus, let's say, strontium, let's do Br2. So if we want to compare these, let's compare them pairwise first, and let's see if we can put them all in order, or using our rules. So if we look at Mg and Ca, Mg so both of these have a plus 2, minus 1 situation for charge. So then we're looking at size. So magnesium is smaller because it is in the 3rd row, calcium is in the 4th row. And so between the magnesium chloride and calcium chloride is stronger interaction. Okay, so we know that the magnesium chloride ion is greater than calcium chloride for predicting strengths. And if we look at rubidium chloride, we know rubidium chloride is less than in either magnesium, calcium, or calcium chloride, simply because it's +1, -1. Now, if we look at strontium bromide is +2, and this is -1. So the same as these two, but it's farther down. So we still have this +2. Now, how much does size play a role and how much does charge? It's not clear. We can say, though, that strontium, black, strontium bromide is bigger than rubidium bromide. And we would expect that we could probably put this here and assume that this is true. That this is strontium bromide. We can kind of order in this way in this pairwise fashion. So know that charge matters most, size matters next if charge is the same.